In the next section, we'll talk about the goal. What types of running times or what types of algorithms for these parameterized problems do we see as tractable, as efficient? And in general, this is a bit up for debate. I'll present the solution that people have come up with because it has led to a theory around these problems, or makes for nice classifications. But it's maybe, as in the case for P and NP, is not without alternatives, or you could debate it a bit. Let's see some examples of what running times one could possibly achieve. So here I'm listing some exemplary problems, and I'm not trying to invent good algorithms. I'm just listing running times for the most shallow, stupid brute force method that just goes through all possible options and checks them one by one. Okay? So don't. I'm not claiming that these are the best running times for any of these problems. If I have the p variables SAT problem, we'll see this in more detail in a second. If I have k variables, the number of assignments is 2 to the k. I can assign each variable to true or false. And then for each of those 2 to the k assignments, I have to evaluate the formula, which is conceptually, I have to replace every variable with its value in the assignment, and then I have to simplify the resulting term. You can be more or less smart about this simplification, but you can do it in linear time if you have the formula parsed, and then you can bottom-up evaluate it. That's not too hard. So that's one type of running time we can get. Another parameterized problem, the p-clique problem that we've seen before. If I were to check in a graph whether it has a clique of size k, the simplest thing to try is just go through all elements, all subsets of k elements, k vertices, and check if all of the k choose 2 edges between them exist. I might do this if I have the graph given as an adjacency matrix. I might do this in constant time for each edge. Then the total time is number of candidates to check times this time for each candidate. And n choose k, a little bit of refresher on combinatorics, not that this is super relevant here. Is this falling factorial k terms? And then we divide by k factorial, which is k times k minus 1 all the way down to 1. And this is asymptotically equal to n to the k divided k factorial, where here this tilde means if you divide this by this, the ratio converges to 1. All that we need to know for this is n choose k roughly grows like n to the k. So it's a polynomial if k is constant, but of course if k is allowed to grow, then this also grows very quickly. That's another type of running time we could get. In a slight variation, if we look for vertex covers instead of cliques, it's a similar game. The vertex cover is a collection of vertices. So if my threshold k means I'm allowed to pick at most k vertices, then I can check all the k vertex subsets and check if they cover all the edges. In this case, the checking part is slightly more costly than before. Here, the checking part only depended on k. Here, it's the entire graph, not just the subset. But I get a very similar runtime in the end. And last, I could have the coloring problem, where I'm trying to assign colors to vertices. And the question is, can I do it with k colors, where k, again, is the parameter? And here, the brute force method of checking all possible colorings of vertices Now this is incredibly wasteful because there's lots of symmetry, but really you can't do that much better unless you try to be really smart. The possible number of candidates to check is every possible color for every vertex. So you have k to the n possible different colorings. Checking them is not so hard, but of course this grows, even for small k, this grows very quickly. And so one way to look at this is to think about what values of k would make the resulting algorithm polynomial time. And so if you look at this part, maybe let's go bottom up, it's easier. This problem, this running time really is polynomial only when k is 1, really. Right? Even for k equals 2, that time would be exponential. Now the question whether a graph is too colorable is actually in poly time, because that's the question whether the graph is bipartite. But that's a different story. And indeed, we know for k equals 3, the problem is NP-hard. So really here we can't hope for much. These kind of running times are a bit less problematic. At least any constant k would still give polynomial time. So we could debate whether these are good or not. Now, if k is a large constant, that's very questionable, but it's certainly polynomial. And the last bit here, we can't make k linear in n for sure, but we could tolerate, for example, logarithmic in n. Then it's still polynomial. So certainly better than this case. You can make it slightly bigger, I guess. Log n times log n is also still polynomial. You cannot allow log squared n, then it would be n to the log n. That's not polynomial anymore. Okay, the exact boundary is not my point here. The question is, which of these running times should we accept as good? Maybe a priori is not even so clear, but you'll see. The definition is essentially drawing the line between those two. The top is okay, and the bottom 3 we don't like. So let me draw this in here. But there's a twist to the definition. So formally, what we like, a fixed parameter tractable algorithm. So an algorithm that we consider efficient for a parameterized problem is defined as follows. We have a parameterization, and we have an algorithm that works on this alphabet. Now, the algorithm doesn't need to know the parameterization. We're just analyzing it using that. And we say the algorithm is fixed parameter tractable if it has this running time. I can somehow split the running time into a product of some part that only depends on k and some part that is polynomial. And crucially, that's also the only restriction we put there. This function of the parameter is allowed to grow as quickly as it can get. Technically, the restriction that it has to be a computable function, but it could be an Ackermann function or anything. It could be completely crazy. And in a way, that's one thing to watch out for. If that function grows beyond any reasonable bounds, maybe the algorithm isn't as useful. But that's the definition that led to the round theory. And in many practical examples that we'll see, f is reasonable. Okay. So again, polynomial in the overall input size, just as before, multiplied by some part that only depends on the parameter, but is allowed to grow as quickly as possible as a function of k as we like. Okay. Then there's a complexity class that goes alongside with this definition. The class FPT contains all the parameterized problems for which there is an FPT algorithm. Hopefully not surprising. You should think of FPT, maybe think of the P here, to play the role of P of efficient algorithms, but with this caveat that because this parameter needs to be chosen and the function of the parameter can be arbitrary, it doesn't always mean polynomial time. Okay, I probably gave this away now. I wanted to ask people before we continue. Without much further and you should essentially answer this question using the knowledge we've covered so far, not using any more sophisticated algorithms that might exist. So show results as a really clear picture. That's right. And so here's the corresponding theorem. It's basically just applying the definition and things I've said before, but good to see that people are following. I just, for specificity, spelled out the actual algorithm. And let's go through this one more time, just to make sure this is super clear. I'm not trying to sell this as an exciting result. You can formulate it as a recursive algorithm. So you're given some formula, and I don't actually care what form it is in. It doesn't need to be conjunctive normal form here. And as a second parameter, just to make it convenient to write down, I'm given the list of variables of the formula. So you would have some pre-processing that extracts all the variables and calls this function. Now, if the number of variables is 0, there's no more variables in the formula, then it has a specified value. It's either true or false. And so I can evaluate it, and this equals is supposed to simplify the formula or evaluate it. So this might not be constant time, right? But it will be at most linear in the size of the formula. If you find the formula is true, then you return the empty set, which is the satisfying assignment for the variables that are still in this formula. And that is empty because there's no variables. Otherwise, we return unsatisfiable because it's just false. That's the base case. If I have some variables, then I'm going to pick the two options for the first variable and recursively solve with both options. So I'm iterating over the two choices I have for x1. Then I'm constructing this partial assignment, just this notation here written as a kind of a function that maps variables to some Boolean value. Then I evaluate the formula with this substitution. I'm replacing x1 by its value. I guess this is logic speak for substituting. The notation is not so important. You basically iterate through the formula, and whenever you see the variable x1, you replace it with the constant value. Then we recursively call this algorithm on this simplified formula and with the set of variables without x1, because that's now eliminated. So we will eventually reach this base case if we do the recursion. And now what we get back from this recursive call is either this flag unsatisfiable, you gave me something that's false, or it's a satisfying assignment. And if it's the latter, then we add our assignment for A, because for x1, because it seems to have led to a satisfying assignment. That's all. Okay? I hope this is roughly what you had in mind when I earlier said we just try all possible variable assignments. You could split it and first assign all variables in one big loop, or in k-nested for loops or whatever. There's different ways to write this down, but that's one rather compact way. If you analyze this, then the worst case running time is the time we need for the base case. That dominates. That's linear in the number of, in the size of the formula. And the number of recursive calls that we make is 2 to the k. In the worst case, we might stop earlier if one of the recursive calls already returns a satisfying assignment. We wouldn't actually try the other option. So it might terminate early, but at most it's 2 to the k recursive calls. And what we're doing in here is also bounded by linear time. So that proves this problem is in FPT, because we found an algorithm whose running time has exactly this form, right? There's a part that depends on the parameter only, and then there's the simplest of all polynomials, the identity function or linear. That's certainly a FPT running time. Now, a problem with this is that the number of variables is probably not small in real instances. If the formula is very big but only uses a small number of variables, there's a lot of redundancy in there. So, I mean, this is a true theorem, but it's not a very useful theorem. It's not super exciting. Okay, this was basically to test out the definitions. Now I want to make one cautionary remark here, that, as I said, the definition of FPT is chosen in a specific way because it makes for a round theory, but it has a few rough edges. And in particular, it means if you pick your parameter sufficiently stupid, everything is in FPT. And by everything, I really here mean everything. So formally, this statement says, if you pick the parameter in a specific way, then any decidable language, anything you could possibly compute on any computer, is actually in FPT. For this specific parameterization, of course, is only the parameterized problem that we're talking about. So what is this this broken way to define a parameter? This is the attempt to make it minimally broken or not obviously stupid. Of course, you can force this by making the parameter just an insanely fast-growing function. But even that is not so easy to do, because what's the worst possible running time any Turing machine can have? It's a side problem that we're not so interested in this class, but this is a busy beaver kind of question. Can you make a Turing machine that produces as many output cells? And this, I think, is an open problem. So maybe it wouldn't even be so easy to write down the worst possible parameterization. But actually something relatively simple and innocent looking is enough. You just need that your parameter is bigger than some function of the input, where this function is weakly increasing. So it means it doesn't go down if you increase the input, and is unbounded. So it doesn't just stop at some constant value. It eventually reaches any possible value. But that second part, I guess, is very natural for most types of parameters. It's the first part that you should be wary about. And we also need this function to be computable, but that's a weak requirement. Okay. The proof is a little technical, but I want to go through it just to illustrate where these things break. I think it's insightful to look at this. Yeah. No zooming, please. I'll try to keep the theorem here. So first of all, if L is decidable, that means there's some Turing machine that, some algorithm that computes it. And we can assume that it has some running time, right? Let's say in time at most t of x, the length of x is the worst case running time. Without loss of generality, I'm assuming that this function is also weakly increasing. And larger than x itself. So these are technical requirements, but they're easy to achieve. You could just take, because we only need an upper bound, you can just take the larger of the size of x and t if it ever was faster. And it's a weird decider that doesn't read the input. And the weakly increasing, you could just take the maximum over all running times up to sizes up to this point. So these are easy to achieve. Now the proof will essentially try to hide this arbitrary running time t in the parameterized part of the function, this f of k part, right? Now the question is how to do this, because all we have is this requirement that the parameter is at least this function g, which, let me stress this again, g could be a reasonable function. It could be log of the size, right? So, or let's be more generous. It could be log of the input size. That would still satisfy these requirements. So the trick to do this is to define some, think of it as an inverse function, is essentially something like an inverse function of g. But because we're dealing with a function that is maybe not bijective, so it doesn't exactly exist, but let me still write this as a function in the parameter just called g as a variable. And we take the largest input n, such that, okay, it's a bit annoying. Let me say g prime, because we also need the function g. That the function g of n is at most this g prime. Now, sometimes this set is empty if there is no n for which this function is small enough. So let me formally take the union with 1. So it's a base case. If your g prime is too small, then h will just output 1. Okay. Let's sketch a bit what this function looks like. And let's start with drawing our function g. It might be low at some point, then it might jump. It might stay constant for a while, but it will eventually go above any kind of bound that you set for it. So say that is g of n. And our function h will be if we put some threshold here of g bar. Our function h would pick the largest n so that g is still smaller than this. So it would pick this one as, that would be, okay, it's inconvenient now. Should have planned better in the drawing. So this is h of g prime. Okay. So it's kind of an inverse function of g, except that because it can jump, it's not necessarily a smooth and doesn't attain all values. But let's collect a few properties of this function h. First of all, because g is weakly increasing, this was from the assumption, and unbounded, we get the same, we get that h is well defined. There's always a well-defined maximum here. How could it not be? Well, then this set would be infinite. That could be how it breaks. But we say g goes above any bound at for some values, so it will always be a finite set of n where g of n is below this bound. That's part one. That's always good when you define something. It's good if it's well defined. H is also weakly increasing. Which you can effectively see from the picture. I mean, you're making this set, if you increase the bound g prime, you're just including more elements in the set, so taking the maximum cannot give you a smaller result. That's, I think, very intuitive. Also, because g is a computable function, we can also compute h. And how would you do this? You can just go by definition. We don't need to be smart or fast. You can just keep increasing n, and if g eventually goes above your bound g prime, then you stop. So again, no claim on the running time. It's just needs to be computable. And now the important part. What if you take, I said it's a somewhat inverse function, so you would expect if this was exact inverses, you should get back n. The way it's defined here, if we insert g of n for g prime, you see that this is really a g of n less or equal g of n, except that the inner n is a free variable. So certainly picking the same n always works, right? So let me write n prime here so that we don't confuse it. Right, if you, it's a greater equal. If you insert g of n for g prime, then you're trying to find the largest n prime so that g of n prime is at least g of n. This is at most g of n. Certainly if you put n prime to n, that always works. Maybe because g is constant for a while, you can put in larger values than n for n prime. That's fine, but it won't be smaller. Okay. And so now the rest is just putting things together. The time to decide whether decide whether any string in our alphabet star is in the language L. Remember, this is what we're talking about. It's we're trying to solve this parameterized problem L kappa. So we're asking, is a certain word in this language L? And I'm claiming that this is an FPT, so that there should be an FPT time algorithm. That's where we are. So the time to do this, by definition, was bounded by t of the size of x. We said that's the definition. T was the running time of this algorithm that decides L. And now we're using that t is increasing, which means I can make the argument bigger and the overall function will only grow. And so we use this and condition 4 to replace, instead of n, let me write n instead of this. So n for the size of x. And this becomes even more obvious. Okay, I'm just inserting. Now I'm using that both t and h are increasing. So I can make the argument inside h bigger and only the bound goes up. And g was a lower bound for our parameter. So if I write k for kappa of x, then that is greater than g of n. And so that's upper bounded by h of k. And then that's all we need, because that is a function just of k. We haven't defined that function, but here it is. Okay? So the overall, the total time that whatever this algorithm is that decides L, however long it takes, we can hide that in a function that depends only on the parameter. If that parameterization is chosen according to these conditions, it's lower bounded by a function that's never decreasing. So whenever you define parameters, you probably need to tolerate that sometimes a smaller problem has a larger parameter than a larger problem. That shouldn't be too surprising or too hard. Okay? So take it as a long caveat to say the theory is a little broken if you allow arbitrary parameters. It doesn't always make sense. FPT doesn't imply anything unless you also pay attention what the parameter is. But for now, let's forget about this. As I said, the definition is to make the theory round, and you have to use it wisely. FPT doesn't even relate to NP in general. Any computable function can be an FPT. Good.